Centripetal acceleration. At Texas Motor Speedway, NASCAR drivers go around this end of the track at speeds of 200 miles an hour, which is roughly 90 meters per second. How would we describe the velocity and acceleration of cars on a turn like this? Assume the cars maintain the same speed as they go around the curve. Are they accelerating? The curve at the end of the track, over here, is like part of a circle. Assuming constant speed, the drivers are traveling in uniform circular motion. The car velocity is always tangent to the track in the curve, and they are accelerating since the direction of their velocity is constantly changing, as shown by the blue arrows. To help explore UCM further, let's use the example of a ball spun in a circle at the end of a string. Shown here is the ball at two different times on its path. There's just one ball here, but here it is at the first time, here it is at the second time. The distance from the center of the circle remains the same, r, as does the time it takes to travel completely around the circle, the period t. If there were no string, the ball would keep moving straight. It would not travel in a circle. Cutting the string at the exact moment that the ball was at the top of the circle, right over here, causes the ball to no longer travel in uniform circular motion. Instead, the ball would go in the direction of its velocity vector at the moment the string was cut. The ball would initially fly horizontally to the right and then fall to the ground in projectile motion. So that would be shaped kind of like that. Which direction is the string pulling in order to keep the ball in uniform circular motion? The string is pulling towards the center of the circle, no matter where the ball is in its circular path. The string is applying a force towards the center. The force providing the acceleration toward the center that stops the ball from flying off in a straight line. It makes the ball travel in uniform circular motion. When an object is in uniform circular motion, its acceleration and velocity vectors are perpendicular. They form a right angle. This will be true for any object in uniform circular motion. It is also the case that if an object's velocity and acceleration vectors are perpendicular, it means that the object is moving in UCM. This kind of acceleration is called centripetal or radial acceleration. Centripetal comes from Latin and means center seeking. Its direction is always towards the center of the circle, no matter where you are there. Its magnitude is v squared over r, where r is the radius of the circle and v is the magnitude of the velocity of the object in circular motion. Let's derive the equation for centripetal acceleration. As the object travels from point A over to point B on the circular path, its velocity vector changes direction. The change in velocity, delta v, is shown to the right. That's this one over here. The vectors v1, v2, and delta v form an isosceles triangle. So starting here, here's the velocity at A, here's the velocity at B. We're going to call that v2, and this is v1. And then we connect those two arrows. We slide v2 over to this point here. Okay, we can do that with a vector as long as we don't change its direction. And we find that we have v1 plus delta v is equal to v2. We do some vector math. So delta v is v2 minus v1. The change in velocity, delta v, shows the direction of the acceleration. As theta gets smaller and smaller, approaching 0, by moving point B, let's look at B again, and point A, we move point B counterclockwise there. Eventually, delta v will point directly to the center of the circle, which is the direction of the instantaneous acceleration. The velocity vectors v1 and v2 subtend an angle phi, and we're showing that over here and over here. As the object moves from point A to B, okay, this time we have A over here and then B over here, it subtends an angle theta right here between the position vectors r1 and r2, also known as the radii of the circle. Since v1 and v2 are both perpendicular to the position vectors, the angle phi is equal to theta. So let's just erase some of this and show that where they're perpendicular. And here we go. This V1 is perpendicular to R1, right over here. V2, okay, that's perpendicular to R2. There's a right angle there, and that's shown here. So we have phi equal to theta. As the angle theta approaches 0, the points A and B move very close together. Then the distance that the object travels between points A and B is essentially a straight line. The distance the object travels is equal to the object's velocity v multiplied by the time t it takes to get from A to B, which is vt. So we now have two triangles, the velocity vector triangle and a position vector triangle. Since they both have the same vertex angle theta, and both triangles are isosceles, they have two sides of equal length, and the other two angles are the same. So the two triangles are similar. Little geometry going on there. Since we have similar triangles, the sides must be in proportion. Please check that out with your math teacher. So we have delta V here over V equals Vt over R. Next we take the definition of acceleration, which is delta V over t. And using this equation here, we're going to put t over here, and v is going to go over here. So we now have delta v over t is v squared over r. Therefore, the centripetal acceleration is v squared over r. A car goes around a circular track with a radius of 82 meters at a constant speed of 38 meters per second. What is the magnitude of the car's acceleration, and what is the direction of its acceleration? We have our givens, and the acceleration is v squared over r. So we plug in 38 meters per second, and we square that term, divide it by the radius, and we get 17.6 meters per second squared. The direction of the acceleration is towards the center of the circular track. A bike going around a circular track whose radius is 63 meters experiences an acceleration of 2.3 meters per second squared. What is its velocity? What is the direction of its velocity? Here's our givens. And first, we will solve the centripetal acceleration equation for velocity. And we get AR equals v squared. Take the square root of both sides, put v on the left, and we have the square root of AR. Bring that here, substitute in our variables, and we get the square root of 145 meters squared over second squared. Now make sure you remember to take the square root, and we get 12 meters per second to 2 sig figs. What's its direction? Tangent to the track. An object is experiencing an acceleration of 5 meters per second squared while traveling in a circle at a velocity of 2.5 meters per second. What is the radius of its motion? First, solve the centripetal acceleration equation for r. Multiply through by r, and we get r is equal to v squared over a. Bring that over here, substitute in our variables, and we get a radius of 1.25 meters.